consider some elevator problems on Unit 4, Worksheet 4. It says an elevator is moving at a constant velocity of 2.5 meters per second. As illustrated in the diagram below, the mass of the man is 85 kilograms. For this purpose, I'm going to use 10 newtons per kilograms. You may find other answer keys where 9.8 or 9.81 newtons per kilogram may have been used. The first thing you want to do is define the system as the man. Next, they ask us to construct a force diagram, and we're going to write down what we know, the given information first. So they told us the mass of the man is 85 kilograms. Oh, and as always, please feel free to watch these faster or slower as necessary. Pardon me. It says that there's a constant velocity, so it's moving at a constant speed, and it says that it's 2.5 meters per second is the constant speed. It just froze on me. We're going to try that again. 2.5 meters per second. Now, at this point, we have to realize that there's hidden information in here. The fact that the velocity is constant actually tells us something about the acceleration. If the velocity is constant, the acceleration must be, and you should have said 0 meters per second squared. And if there's no acceleration, that means the net force is 0 as well. 0 newtons. Next up, here comes that force diagram for the person. So we'll draw our force diagram. What's pulling down on the person? We've got a force of gravity on the man by the earth, and the same size upward force, force normal on the man by the floor, and let's say up is positive, down is negative. And they want us to find out that force normal. So in our find and given information, they want us to find the force normal on the man by the floor. Notice I'm missing some vectors there, and there, and there. Great. So how do we find the force, the normal force on the man by the floor? Well, one thing we could do is realize that that's the same size as the force of gravity, because the net force is 0, even though it's in the opposite direction. But to figure that out, we'll have to figure out the man's weight. So to figure out the man's weight, we can do G sub E times the mass of the man. We said we were going to use 10 newtons per kilogram times the mass of the man is 85 kilograms. But before we go on, we have to remember that we said that gravity was pulling in a negative direction, which means this needs to be a negative 10 newtons per kilogram. And that gives us a result of force of gravity on the man by the earth. 85 times negative 10 is negative 850 newtons. Now that we know that, we can use the concept that the net force is the sum of the forces, which means the net force is that upward force normal on the man by the floor plus the downward force of gravity on the man by the earth. And we know already that the net force is 0 newtons. If we just calculated the weight of the man down here, so that's negative 850 newtons, and that can help us find the force normal. So how do you get force normal by itself? Well, we have to get rid of that negative 850 newtons, so if you add 850 newtons to both sides, you now end up with the force normal on the man by the floor is equal to a positive 850 newtons. This is an equilibrium problem, just like we did in Unit 3, Worksheet 5, equilibrium problems. In review, what did we do? After reading the directions, we defined our system. We wrote down the given information of what we were supposed to find. We built a force diagram and defined direction. Then we calculated the weight of the man using gravitational field strength constant times the mass. And then we found the normal force using the idea that the sum of the forces, or net force literally means the sum of the forces. And so that was the steps we go through. It is possible that in some other problems, maybe you'd be given the normal force and you'd have to use this part over here to find the force of gravity, and then pull that back over to here to find the mass of the system like we did in previous problems. So that's problem number 1. Well, how is this important with what we've been studying recently? Let's move on to side 2. Number 2, it's the same man in an elevator, but now he's accelerating upward at 2 meters per second squared. They want us to construct a force diagram for the man, and they want to figure out how much the floor exerts on the man again. So again, we need to start with the given information. Because we knew the mass of the man was 85 kilograms, and because this is the same man, it's on the same page and everything, we can go ahead and write down that his weight, force of gravity on the man by the earth, is negative 850 newtons, because we just calculated that. But in here, we now know that the acceleration is 2 meters per second squared. And they want us to find the normal force. Find force normal on the man by the floor. Oops, by the floor. So, force diagram. The weight of the man has not changed. So the force of gravity on the man by the earth is still equal to negative 850 newtons. Now, what about the normal force? If the man's accelerating upward, if we decide that we're going to define direction on the force diagram the same way, and down is negative and up is positive, is the upward normal force on the man by the floor going to be bigger or smaller than the weight of the man? Well, would someone's weight really change if they were just going up and down in an elevator? And the answer to that is no. So, if the man is accelerating at 2 meters per second squared and it says accelerating upward, if we define upward as positive, this has to be a positive 2 meters per second squared. If you're accelerating upward, there also has to be a net force. What direction does that net force have to be? If you're accelerating upward, the net force has to be upward. So I'm going to measure the force of gravity with my fingers, and now I'm going to draw my normal force bigger than the force of gravity was. And it does not get a hash mark because it's not the same size as gravity. Typically, what students would do at this point is they would say, well, let's see if we can find that normal force, and say the net force is equal to force normal on the man by the floor plus the force of gravity on the man by the earth. We already know that the weight of the man is negative 850 newtons. Do we know the net force? Not anymore. Do we know the normal force? We don't. So, what do we do now? Well, we're ultimately trying to find the normal force. So the question is, can we find the net force some other way? Well, we learned in Newton's second law with the cart and the string and the hanger program, right? We did that, Newton's second law, part 2, part 3, all those good parts, and we found out that acceleration is equal to the net force divided by the mass of the system. Well, couldn't we solve all of this for net force? And if we did so, how would we get net force by itself? We'd have to multiply both sides by mass of the system. So those would cancel out over on that side, and now we've got mass times acceleration is net force. So I'm going to use that formula next. So we can say that the net force is the mass times the acceleration. The mass of the man was 85 kilograms. The acceleration was 2 meters per second squared, and that's a positive 2 meters per second squared. 2 times 85, that's 170 newtons. Kilograms times meter per second squared. And again, this is a multiplying by a positive 2 meters per second squared. So that's our net force. So where can we plug that in? Right here. So the net force is 170 newtons. And now we can solve for the normal force. To get normal force all by itself, we have to get rid of the 850 on the right side, so we have to add 850 to both sides. So we now have force normal on the man by the floor is equal to 1,020 newtons. Again, some of the answer keys online, I might have used 9.81 newtons per kilogram, so the weight of the man might be a little bit off, or it might be different, 9.8, 9.81. But again, in this problem, we defined the system. We wrote down the given information of what we needed to find. We drew a force diagram, labeled the parts and any values that we knew. Even though we attempted to use the net force as the sum of the forces first, that didn't work out, and we had to. We realized that we could calculate the net force another way before plugging that value in here. For all of the problems that we're going to do in this worksheet, you're going to need these two equations. Net force is the sum of the forces, and net force is mass times acceleration, along with how to calculate the weight of an object to solve the problems. I'm going to encourage you to pause the video at this time and go ahead and try problem 3 on your own, and then take a look at the next video for results.